The scan is still running. 30% complete. A pale square sits near the outer edge of the Oort Cloud grid, while the observatory waits for the next refresh cycle. Then the incoming trajectory appears. Not after the observation. Before it, the telescope has not confirmed movement yet. The imaging pass is still collecting the data that is supposed to prove the object changed position at all. But the tracker redraws the path anyway. Quietly. As if the tracker trusts its own prediction before the telescope finishes seeing the object at all. A faint square sits near the outer edge of the Oort Cloud tracking grid, small enough to vanish between refresh cycles. The map is almost empty out there, just black space, distant coordinate lines, and one pale marker sitting thousands of times farther from the sun than Earth. Then the marker shifts. Not far. Just enough to force the tracking system to redraw its projected path before the scheduled observation cycle finishes. The scan was still collecting confirmation data. Operators keep watching the grid while the system quietly updates the object label from unresolved movement to incoming trajectory. No one has confirmed motion yet. The telescope is still collecting the data that is supposed to prove the movement happened at all. But the tracker moves first. For a few seconds, the room becomes strangely procedural. No alarms. No voices. Just status windows opening across dark monitors while the object receives an official tracking designation before anyone can directly verify what changed. A single dot jumps on a dark outer system map. If the motion is real, the scan should complete before the prediction updates. Instead, the prediction arrives first. The system behaves like the object already exists in a stable path the observers have not actually seen yet. For the first time, the prediction layer is behaving like the observation is late. At that distance, nobody is looking at the object itself. Human perception has already been reduced into interpretation layers, correction software, and confidence weighting. The machine decides what counts as movement long before a human being can recognize anything on the screen. The Oort Cloud tracker marks movement too early. And once the update becomes official, every later observation starts inheriting the same assumption. Technicians begin replaying older outer system survey frames across multiple monitors. Different observatories, different years, different imaging systems. At first, nothing looks unusual. Just dim telescope captures filled with static stars and scattered light distortion near the edge of deep space surveys. The kind of archive footage nobody manually reviews unless software flags it first. Then one frame pauses. A faint point receives a motion tag matching the new incoming trajectory. Nobody in the room reacts immediately. The image is years old. The object was never identified during the original survey. But once the modern detection enters the tracking system, older frames start reorganizing around it. Ancient telescope images flicker one after another, while a single trajectory line slowly connects them. The object now looked permanent. For several minutes, the review becomes almost mechanical. Operators move frame by frame through archived observations, while overlay software redraws projected paths across old star fields. More matches appear. Another observatory confirms the same reconstruction. Then another. Old Oort Cloud survey frames begin agreeing backward. That is what changes the situation. If the object was truly invisible before, the old surveys should remain uncertain. Instead, the archive begins producing coordinated evidence only after the modern detection exists. The system is no longer just observing motion. It is deciding which forgotten points inside years of uncertainty now count as meaningful. The first marker no longer looks isolated. It starts looking like the moment the archive began reorganizing around the object. And because no human being can manually verify years of astronomical imaging across multiple observatories, the reconstruction becomes trusted almost immediately, even while confidence inside the room quietly begins collapsing. Internal observatory dashboards begin syncing across multiple facilities. One by one, isolated detections from different surveys collapse into the same projected path. What looked scattered a few minutes earlier now moves with quiet consistency across the screen. A dark observatory interface where scattered, faint detections suddenly align into one clean incoming arc. An analyst zooms into the motion filters instead of the archive itself. The overlays become denser. Noise reduction passes stack on top of long-range prediction models. Older survey frames slide into alignment around the incoming trajectory almost immediately afterward. Then he says it plainly. The archive itself had not changed. The filters were... For the first time since the first marker appeared, the room stops feeling unstable. The explanation sounds operational. At Oort Cloud distances, direct visibility is almost useless. Tiny shifts in movement have to be reconstructed across years of faint observations and predictive tracking layers before a coherent object can emerge at all. The tracking system finally makes the path look explainable again. And for a moment, everything begins fitting together again. If the object was always too dim for conventional detection, then the earlier retroactive matches are not evidence of corruption. They are evidence that the system was sophisticated enough to identify a trajectory humans could not recognize alone. The analysts continue overlaying older observations into a unified motion model. No panic, no argument, just synchronized interfaces slowly narrowing uncertainty around the incoming arc. Human beings were never manually tracking this kind of distance in the first place. They were trusting invisible interpretive systems long before the anomaly appeared. And now the same system that nearly broke confidence is becoming the only reason the object still feels understandable at all. Incoming trajectory maps refresh again after the newest observation pass completes. For a few seconds, the display looks cleaner than before. The incoming arc sharpens across the outer solar system map, while prediction overlays tighten around a single projected route. Then the path divides. Not into noise, not into random scatter, into several stable incoming trajectories, each one internally consistent, each one carrying nearly identical confidence ratings. Several glowing trajectory lines slowly spread apart across a dark solar system map, while confidence indicators stay green. Nobody speaks at first. Analysts continue feeding new observations into the tracker, as if the divergence will correct itself on the next pass. Instead, every update increases the separation. Tiny angular uncertainties near the Oort Cloud begin expanding into enormous projected differences farther inward. The Oort Cloud path splits instead of narrowing. That is the moment the explanation from earlier starts breaking apart. If newer observations improve precision, the trajectories should converge toward one stable solution. Instead, the correction passes produce cleaner disagreement every time the system refines the object. The predictions become more coherent, while the object itself becomes less certain. The confidence scores stayed high. One technician quietly compares earlier outputs side by side. The system never signals instability. It behaves as though improved prediction and expanding contradiction are the same thing. For a moment, the room becomes strangely calm again. Just dark interfaces, synchronized observatories, and glowing trajectory models slowly drifting away from each other while every indicator continues reporting success. The tracker is no longer failing in obvious ways. Every correction pass looks cleaner, while the object itself becomes harder to pin down. The newest dashboard refresh is almost calm. One trajectory remains highlighted across the outer solar system map, while the surrounding prediction layers settle into clean, geometric shapes. The divergence from earlier appears contained now, stable, procedural. Then the confidence overlay shifts. Not toward the object, toward the tracking architecture itself. A dark solar system map where the confidence overlay detaches from the object trajectory and wraps around the tracking architecture itself. Nobody notices immediately because the incoming path still looks coherent. Analysts continue refining observation timing across synchronized systems, while the network keeps increasing certainty around its own correction behavior. The Oort Cloud tracker becomes the anomaly. One technician isolates the oldest unprocessed observation from the original detection cycle. No predictive filtering, no correction layers, just the earliest raw signal before the tracking network began rebuilding trajectories around it. The oldest signal matched nothing else. For several seconds, the room stops moving. The raw observation sits outside every modern prediction layer now considered reliable by the system. The newer corrections no longer converge around the original object position. They converge around each other. That is the contradiction nobody can comfortably explain. If the tracker is improving accuracy, the later models should move closer to the first observation. Instead, the first observation becomes increasingly excluded as the system refines itself. Months can pass between direct confirmation opportunities at Oort Cloud distances, but the prediction systems continue evolving in real time the entire way. Quietly, continuously, building confidence faster than reality can answer back. And suddenly the first unstable marker from earlier no longer looks corrupted at all. It looks like the last moment before the tracking process started teaching itself what to believe.